Okay, so today we're going to start on thermal properties of matter, chapter 9. So we're left with a few more sessions. So let's carry on. Okay, so under thermal properties of matter, this is the last part of the thermal physics. So we went through kinetic model of matter, we went through transfer of heat, then now we are down to chapter 9, thermal properties of matter. Okay, so in this chapter, okay, what we're going to do is we're going to look at how temperature is related to this concept called the internal energy of matter. Okay, and we're going to explore what happens during a change in state in terms of the molecules. Then the last part really is about how different is the evaporation compared to boiling. Okay, so we're going to compare these two. So under this chapter, these are the three big things that we'll be looking at. So now, first things first, internal energy. So just take note of this. Okay, whenever a substance, or whenever any substance gains thermal energy, okay, so what happens is that this will result in an increase in the internal energy of the substance. So what happens is that when, for example, when a beaker of water, so the water is over here, when the Bunsen burner is heating up the heater, so the thermal energy from the flame actually is transferred to the water, and the internal energy of the water increases. So as what I mentioned, when substance gains the thermal energy, it actually causes an increase in the internal energy. And because internal energy is a form of energy, that's why the units is still in joules. I just want to highlight that in this chapter, really there isn't any formulas in terms of calculation, okay, for the combined science students. So just take note of this. Okay, so what exactly is internal energy? So as mentioned here, the particles in substance are in continuous motion. Okay, this is actually stating the kinetic particle theory. Okay, and there's also attractive forces that exist between these particles. And because of the continuous motion, anything that's moving, it has speed. We talk about it having Ke. The attractive forces is sort of like a stored energy. That's why this is really looking at in terms of the Pe, or potential energy. And these attractive forces, what we're looking at is the interatomic or intermolecular bonds. So these two add up, the Ke and the Pe actually results in what we call the internal energy. Okay, so as what they're going to mention here in the next part, figure 9.2, it shows the internal energy of a substance is the total. Okay, so this is actually the definition. The internal energy of a substance is the total energy of all the particles in the substance. So what are the what does the total energy comprises of? Okay, so they mentioned it comprises of two main components, which I already mentioned here, but let's look at the next diagram. So the internal energy, which is the total amount of energy in the substance, it can be broken down into these two parts here. One is called the internal potential energy. In short, I'm going to write IPE. And the next one is the internal kinetic energy, IKE. Okay, so I'm going to refer to internal potential energy as IPE subsequently, and internal kinetic energy as IKE subsequently. So what exactly is internal potential energy first? So we do know that because of the intermolecular force of intermolecular bonds or intermolecular force of attraction, or it is stretching and compression. Actually, I tell you, it sounds very cheap, but you can actually go and take a look, Google up the diagram. Okay, the bonds actually doesn't, it's not a fixed, kind of like doesn't lock the molecules or the atoms in position. It actually just makes sure that when they go too far away, it pulls them back, or when they are too near, okay, they actually start to like move further apart from each other. And this stretching and compression due to the bonds, okay, is actually the amount of potential energy that it has, okay, that is being stored. So this depends on two main things here. Okay, first is the forces between the particles. The stronger the force, okay, it will cause the change in potential energy. How far they are also cause a change in the potential energy. So this is about the internal potential energy. In terms of the internal kinetic energy, as mentioned, this is due to the motion of particles. Okay, so in terms of the motion of the particles, what we're looking at is in terms of how vigorous the particles are moving. Okay, I say again, it is in terms of how vigorous the particles are moving. So temperature, okay, is really linked to the movement of the particles. Internal potential energy is really linked in terms of the bonds. Okay, so the forces of attraction and how far they are. So do take note of all this. Okay, so internal energy of a substance can be broken down to IPE, IKE. IKE is really due to the particle movement. Alright, particles movement, which is linked to the temperature. Right, this one is really linked in terms of the how far the particles are. It is far, how far the particles are, which then is due to the force of attraction. Right, force of attraction, or sometimes they'll call it the bonds. Okay, so this one is how they're related together. So let's go on. Okay, so in terms of this 9.1, I just want to highlight that what we have mentioned is really the internal energy comprises of KE and PE. This second key idea is really linked to what we have covered in the kinetic model of matter at the very last part, where we say when temperature increase, okay, what's going to happen is that the average KE will increase. Average KE of the particles will increase, which will lead to an increase in the average speed of the particles. So this one is sort of like mentioned in your chapter 7 actually. Okay, now let's go on to 9.2 now. So what we're going to cover in 9.2 is really what happens during melting and solidification. Another word for solidification is actually also freezing. Right, so we're going to look at this two a little bit more in details. So what exactly is melting? I want us to take note of this. Okay, many of us know that a change from the solid state to liquid state is called melting. But I want you to take note of this. During melting, the temperature of the substance actually does not change. Okay, so I want you to put a star over here. Do take note, during melting, okay, the temperature of the substance actually does not change. And this is a very important concept here. Okay, and I know many of us think that melting only occurs at 0, which is because of ice. However, do take note, different substances have different melting point. Okay, so please do not assume that every single thing melts at 0. It's not true. So this is an experiment, okay, regarding how to determine the melting point. I won't really go through it. I want us to really look at in terms of this curve. Okay, this one. Okay, this is what we call the heating curve. Why we call it a heating curve? Because what is happening here is actually the ice is being heated, and the ice is gaining heat, and the ice melts into water. Now, before we go into this, okay, I want you to look at this experiment a little bit. What you realize that the Bunsen burner is heating up the ice all the while. So from the start all the way to the end, okay, so I'm going to use a different color now. I use pink. From here all the way here, I need you to take note of this. Okay, is that the substance, which is the ice, is being heated throughout. So the substance is being heated throughout the entire experiment. So this is something that I need us to really be aware of. But of course the question comes in is, sure, if the whole thing is being heated throughout, how come like there's this very weird part? Okay, so let us look at it in details now. So in this whole graph here, we actually can split it up into 3 main portions. Segment 1, segment 2, segment 3. So what exactly is happening? So from P to Q, okay, the graph is a curve. What is happening is that the temperature of the ice rises from -15 to 0. Okay, there's a change in temperature and no change in the state. Now this is the tricky part. Okay, sorry, let me meet somebody first. Okay, so why I say tricky here? Because many people always have the misconception that ice must be at 0 degrees Celsius. That's not true. Ice melts at 0 degrees Celsius. Water freezes into ice at 0 degrees Celsius. But ice can actually go below 0 degrees Celsius. So I want you to take note of this here. Okay, to just cast away that misconception that ice must be at 0. Ice can go below 0 degrees Celsius. Okay, now, so part 1 says there's a change in temperature, no change in state. I want you to take note of these two statements here. Later on, I'll come back into it. So from P to Q, the ice is gaining heat. The temperature increased from -15 to 0. There's a change in temperature, but there's no change in state. So during this point, the ice remains as ice. Okay, it's still in a solid state. Now, what happens between Q to R? The weird thing is that you can see temperature doesn't change. From Q to R, the temperature remains constant at 0 degrees Celsius. And what we know is that 0 degrees Celsius is actually the melting point of ice. So what exactly happens? From Q to R, the graph is a horizontal straight line. Temperature remains steady or remains constant at 0 degrees Celsius as the ice melts. This happens in spite of the thermal energy being absorbed. So what they're trying to say is at this part here, even though the temperature is at 0 degrees Celsius, thermal energy is still being absorbed. Okay, so you need to be aware of this. Thermal energy is still being absorbed. Same statement here, except that there's a change. So here it says no change in temperature, but there's a change in state. So comparing 1 and 2, you realize that change temperature, no change state. No change in temperature, change in state. It feels like when one happens, the other one doesn't have anything happening. Okay, I will go through a little bit more in detail as mentioned just now. And last part, R to S. What's happening is that from R to S, the graph is a curve. Okay, when the ice has melted, so at this point, all ice has melted. So once there's no, has melted, not melting. All the ice has melted. So once all the ice is melted, it's become water already, the temperature will start increasing again. So all ice melted, the temperature of the water, which is the liquid, rises from 0 to 10. At this point, there's a change in temperature. There's no change in state. Okay, so now, I've asked you all to underline all these things. What's actually happening? So I need you to take note of this. Okay, write it down carefully. Whenever there's a change in temperature, so I say again, when there is a change in temp, comma, there will be no change in state, and vice versa. Okay, so I say again, when there's a change in state, when there's a change in temperature, there will not be a change in state. But when there's a change in state, there will be no change in temperature. So they will only change one of them at a time. It's either temperature change or the state changes. Okay, only one of them will change at a time. So what exactly is happening? Throughout the whole thing, okay, I just want to highlight here, substance is heated throughout. So the water is gaining internal energy. So throughout the whole time when the substance is being heated up, when the water is being heated up, the water is actually gaining internal energy. Okay? Two things can happen. This internal energy can either be converted into the internal kinetic energy, or it can be converted into the internal potential energy. It can only convert into one of them at a time. Okay, in your syllabus as mentioned, okay, I'm going to say this again, so listen up carefully. When the water gains internal energy, when the water gains internal energy, this internal energy can either become IKE or IPE, only one at a time. Okay, now, and I need to take note of this. Internal kinetic energy is linked to temperature. Internal potential energy is linked to a change in state. So with that, with this basis, now if we come back to this 1, 2, and 3, so what exactly is happening? When there's a change in temperature, what's happening is that the internal energy is being converted into the internal kinetic energy. Okay, the gain in internal energy is all because of IKE. There's no change in the IPE. Okay, so take note of this. At part 2, what is happening is that there's no change in the temperature. That means actually there's no change happening in terms of the internal kinetic energy. So all the internal energy that's being absorbed is not converted to kinetic. All the internal energy absorbed is actually converted into the potential energy. Okay, so you must be very very familiar, okay, or you must get used to the terms of kinetic energy and potential energy and what they are linked to. And of course, the last part, when there's a change in temperature, what it means is that internal energy is converted into the internal kinetic energy. There's no change in the internal potential energy because there's no change in state. So state is linked to potential energy. Temperature is linked to kinetic energy. So if there's a change in temperature, there's a change in kinetic energy. If there's a change in state, there's a change in potential energy. So you must be very clear in terms of what is being, how the internal energy is actually being converted in terms of whether is it the KE or PE. Okay, so with that, now let's really look in terms of the explanation. So what exactly happens when the solid melts? So I want us to look at this portion over here. So when there's a change in state, so the portion labeled QR is actually talking about the change in state. In this case here, we are really looking at in terms of this process of melting. So the thermal energy absorbed is actually used to break the strong bonds between the particles of a solid. So if I were to just get the key idea here, is that the energy absorbed, okay, is used to overcome the force of attraction. Okay, so I'm just trying to generalize it. Okay, so the thermal energy absorbed, so the energy that's being absorbed is used to break the strong bonds. Okay, the bonds is actually the force of attraction. So energy absorbed is used to overcome the force of attraction. At this point, what did they say? Only the total internal potential energy of the particles is increased. So what I can add on, the next point is the IPE increases. Okay, the IPE increases. Sorry, let me write this nicer. So energy absorbed is used to overcome the force of attraction. The IPE is increases. So what is actually happening here is that the let's see the particles. Okay, let's not use the particles. The spacing between the particles increase. Okay, because there's a change in state. Hence, there's a change in state. What I'm trying to do here is actually to sort of like generalize this whole description. Okay, so whatever they're describing here, I actually also try to link up to here. So what exactly happens during melting is that the thermal energy absorbed is used to overcome the force of attraction. This actually causes the internal potential energy to increase. And what exactly happens when the internal potential energy increases? It actually causes the spacing between the particles to increase. And as such, there's a change in state. So 4 main points here to describe the process of melting. Whatever that I mentioned there is actually highlighted here. Okay. Now, a common question that exams like to ask also is, why does the temperature remain constant? Okay, so I want you to take a look at this part in blue here. So there are three main points. Why did the temperature remain constant? So there's no change in temperature, right? So this is the point that they're trying to illustrate. So why? Because none of the thermal energy supply is converted to internal kinetic energy. So when none of the thermal energy supply is converted to internal kinetic energy, this means that the particles also are not moving faster than before. So the 1, 2, 3, if I were to rephrase it, okay, so instead of going from top to bottom, I'll go from bottom to top. So I'll say that there's no change in temperature because none of the thermal energy supply is converted to internal kinetic energy, which also means that the particles are not moving faster than before. Okay, so just take note of this. Okay, so let's go on. Now, you can read up more into here, but I felt that there's too much details here. If you were to write down all this in the exams, it's just way too much. Right, so it's either these 4 points whenever you're talking about change in state, or these 3 points here if they're talking about trying to explain, or when you're trying to explain why the temperature remains constant. Right, so let me use my green color pen to just highlight. So this one is the description or change in state. What to write. These 3 points over here is to explain why temperature doesn't change during a change in state. Okay, so for thermal properties of matter, these 2 questions always like to come out. So you need to be able to write the correct thing in. Okay. Now, next part is solidification. It's actually the other way around. So the reverse process of melting is called solidification. I think many of you would know this as freezing. Okay, most of you will term this as freezing. So the temperature at which the substance freezes, we of course call it the freezing point, or sometimes you will see it's called the solidification point. It's kind of weird, but okay, whatever. Okay, so do take note, pure water freezes at 0, which all of us know, but it doesn't mean that every single thing freezes at 0. Different substances have different freezing point. So do take note of that. So what do? Okay, they will actually find out what's the freezing point of the substance through the experiment. Go and read up more on it. Key idea, this graph is the opposite of the one we have gone through. So the previous graph we have seen is actually called the heating graph. This is actually now known as the cooling graph. Okay, because you can see the general trend is temperature is decreasing. So what's happening from the start to the end? Okay, I just want to highlight from the start to the end, the substance is losing heat or losing energy to the surrounding. Right, so do take note of this. Right, throughout the whole entire duration from A all the way to D, the substance is actually losing energy to the surroundings. So let's go through each part here. So there's total, if you look at it, okay, there's actually 3 main segments, 1, 2, and 3. So let's go through them. So first up, region 1 from A to B. So the graph is a curve. Right, the graph is a curve. So what's happening here? As phenethylene cools, the temperature of the substance falls from 90 degrees to 79 degrees. Actually, you realize there's one bullet point that's missing over here compared to the heating graph. Actually, what's happening, you will see that there's a change in temperature, but no change in state. It's very important because you realize that what I mentioned before was that internal energy can only focuses on the KE at one time, okay, or the PE. Okay, it will not have both happening at the same time. So in this case here, there's a change in temperature, so definitely there's no change in state. From B to C, what's happening is that there's a horizontal straight line, means that the temperature remains constant. What's happening is that now there's a change in state. Okay, change in state. Change in state is happening, but there's no change in the temperature. So change temperature, no change state. Second part, change state, no change temperature. And the last part from C to D, there is a curve here. When all the naphthalene has solidified, the temperature of the substance, okay, temperature of the solid naphthalene falls again. So in this case here, there's a change in temperature, but no change in state. So what exactly is happening throughout all this whole thing here? Right, we can see next part, we're going to look at the description itself. So the description actually happens here. So this one is actually just a little bit lost to just tell you what's happening. But this part here, okay, tells you what really happens. So I'm gonna once again write down the summary points. So first thing, okay, I want us to look at this. So I want to really look at the put both together. So for heating, we say thermal energy absorbed used to overcome the force of attraction. Because heating, energy is absorbed. But when you are cooling something down, the thermal energy is released. Okay, so let's start off with the first part here. Thermal energy is released to the surroundings. And when this thermal energy is released to the surroundings, what actually happens? Okay, the forces of attraction they say strong bonds are formed, but I'll use the forces of attraction are strengthened. Okay, strengthened. So this is the first part. So when you release the thermal energy to the surrounding, the force of attraction becomes strengthened. Okay, so really look back, I want you to see really is a comparison. So one is overcome force of attraction, the other one is because I release the force of attraction is strengthened. Now IPE increase in heating, so obviously here we will say that IPE decreases. Now if the internal potential energy decreases, what's happening to the spacing? So the spacing between particles decreases. So when the spacing between the particle decreases, okay, so we say the spacing between particles increase, right? Or down here we say the spacing between the particles decreases, and hence there will also be a change in state. Now I want to circle this change in state part. Okay, because I write here change in state is a very general idea. In this case here, you should be writing the substance changes from liquid to solid. At the top there, you should be writing the substance changes from solid to liquid. So these are the 4 points. I'm purposely trying to scroll up and down to show you that these points are actually very similar. It's just the opposite of one another, because solidification versus melting, they are really the opposite processes. Okay, so this is the description, okay, that you need to write when you're talking about change in state. And once again, you look at this part here, okay, since the internal KE doesn't change, temperature doesn't fall, okay, so this part here really explains in terms of the KE. Alright, to explain the internal, to explain in terms of the temperature not changing. Now I just want to highlight that this part here is exactly the same as the top. I'm not going to repeat that whole thing again. So just take note of that. Okay, you can read up more here to just really understand what exactly is happening stage by stage. So next up, okay, let's look at the key idea here. So we did mention that melting takes place when energy is absorbed. This causes a change in state from solid to liquid. Do take note, there's no change in temperature. Okay, so what exactly happens during melting is that the thermal energy absorbed is used to overcome the strong bonds between the particles. Solidification is just the opposite. Okay, the temperature at which solidification happens, we call it the freezing point. Okay, do take note, the melting point is also equals to the freezing point. So these are the key main ideas that we went through at the top. So now let's go on to the next part. So we talk about freezing, we talk about melting. Now we're going to look at boiling and condensation. So some of you say, sure, isn't boiling condensation most probably going to be the same explanation as melting and freezing? My answer to you is yes, but there's some slight differences. Right? The graph looks exactly the same once again. Right? The graph looks exactly the same once again. You read the description here, it's the same thing again. Now, but there's one part I need you to take note here. When you talk about boiling, it's not just about increasing the spacing. So look at this description here. I want to look at the heating part first. So thermal energy. So if I'm melting, you hear the description. Thermal energy absorbed, overcome force of attraction. IPE increase, spacing within particles increase. So that's why it's changed from solid to liquid. For boiling, okay, this is what the description is gonna be. So there is one additional part that you need to take note. Energy is actually required for the molecules to push back on the surrounding atmosphere. So then, okay, then like that, then how do I write the answer? Can I like just copy and paste the one that is from the top? Is there any way to simplify it and to just make it easier? I memorize one thing, just have a little bit change, and I can answer for both. The answer is yes. So for boiling, okay, do take note of these few points here. So I'm going to write down the same few points, but I'm going to show you where the change occurs. So we will say that during boiling, thermal energy is absorbed, okay, to overcome the force of attraction between the particles. Okay, this is where the little change occurs. I'm going to write in pink. Plus, okay, push back on the surrounding atmosphere. So this pink color part is the additional change that you need to write for boiling. Okay, so once you are done with this pink color part, the rest of it remains the same. So in this case here, IPE increases. 3, spacing between the particles increases. Hence, fourth part, there's a change in state. So what I'm doing here is showing you that actually the description is exactly the same. Just that, okay, you need to add in this part here in pink because boiling requires an additional step, which is to push back on the surrounding atmosphere. Okay, so this is the additional description for boiling, and you realize that, oh, condensation, seems like they never really talked about it, because condensation, it's really not that simple to explain. So in general idea, what would they normally ask you to describe? They'll ask you to describe, so I'm just going to write here, melting, freezing or solidification, plus boiling. So these are the three main processes that they will ask you to describe, okay, in terms of the thermal properties of matter, exam questions inside your tests and exams. But really, if you ask me, is it really very difficult? Answer is no, because you realize there's a sort of like a standard template to use and to answer the questions. Okay, so that's about it. Okay, so you must be able to describe the change in state, what exactly is happening. Plus, you must be able to describe the flat part. Okay, why is the temperature not increasing? So these are the two common questions that likes to come out. And of course, the last part is when the temperature increases, what exactly is happening. So three things are: 1, describe the change in state. 2, explain why no change in temp during change in state. And the third part is to explain Y, change in temperature. So these three parts are, okay, so you must be able to explain all these three parts here. Okay, so that's for until here, right? 9.3. Now let's go on to the last part, which is 9.4, evaporation. Now for evaporation, I think many of us are very clear what evaporation is. Okay, it's different from boiling. Okay, and the differences they like to test lah. So exam questions so far that we have noticed is that they never ever ask you to just write the differences between boiling and evaporation just like this. Okay, normally it's in an MCQ that they'll ask you for the difference, or they will just normally it's MCQ lah. They will ask. So which are the common ones that we will always see? This one. So one of the key difference between boiling and evaporation, that boiling occurs at a particular temperature, which is the boiling point. So which is a fixed temperature. Right? The particular actually just means it's a fixed temperature. Whereas for evaporation, it occurs at any temperature. Okay, so evaporation occurs like in low temperature or higher temperature. Yeah, it just happens. It's relatively fast for boiling because energy is being supplied there, relatively slow for evaporation. But this one is a side point I think most of you know. Next one, really I need to take note is the when during boiling actually occurs throughout the liquid. Okay, so when boiling occurs, all the liquid within the substance is actually changing into gas. Okay, whereas when during evaporation, only the surface, okay, the particles there are changing from liquid to the gaseous state. Bubbles is just an effect because of the gas. Temperature remains constant during boiling. Okay, that's why it happens at a fixed temperature. Whereas during evaporation, the temperature may change. Generally, when during evaporation, actually the temperature of the substance decreases. Do take note of this. Right, so I repeat again. During boiling, the temperature generally remains constant at the boiling point. During evaporation, it actually causes the temperature to decrease. So we're going to look at these 3 points here. In particular, actually the last point that's being mentioned here. So how does evaporation occurs? This one, I'm very sorry, they like to test, they like to ask you how evaporation occurs. Okay, so 1, 2, 3. Okay, I say 1, 2, 3. What do you need to write? First thing, the molecules in liquid are always moving randomly at different speeds. Okay, all those in bracket you don't really need to write. So the first part, whenever you need to describe evaporation, how does it occur? First thing is actually to say that the molecules in liquids are always moving randomly, but the molecules are moving at different speeds. This different speed part is important, right, which we're going to look at it at a later part. So part 2, at the surface, some of the liquid's molecules have enough energy to overcome the downward attractive forces of the other liquid molecules. Okay, so they are able to overcome the attraction between the other molecules. But on the other hand, there's one more part here, is that it's able to overcome what we call the atmospheric pressure. So those with enough energy to overcome them, they escape. Okay, they escape into the atmosphere. Once they escape, what's going to happen is that the less energetic molecules are left behind. What this means is that the average Ke decreases, which means that the average temperature decreases. So this part 3 here tells you that, oh, sure, because the more energetic molecules have escaped, I'm left with the less energetic molecules. What this would also means is that the temperature decreases. So evaporation actually causes cooling, okay, which is the next part that we're going to see. So this 1, 2, 3 here, do take note, okay. The description is quite a fair bit, so my suggestion is actually go and practice a little bit. Try to, if you are able to get a flow of it, the memory work will not be that much. But of course, if you are unable to get a hang of it, then it will be pure memory work. So my idea is just try to understand what exactly is happening. Right, the points are actually quite okay, if you ask me. I think the points are really quite okay to understand. So do try to understand it. Don't blindly memorize this. Okay, so during evaporation, molecules are always moving randomly at different speed. Because they're moving at different speed, those at the surface with enough energy to overcome the downward attraction, to overcome atmospheric pressure, they escape. So the more energetic one actually escapes. So leftover ones at the bottom are the less energetic, which means average KE is actually lesser. Because average KE lesser, the temperature actually drops, which means that evaporation causes cooling. Okay? Evaporation causes cooling. So with that, ta-da! We have actually come to here. Okay, so for this part here, this is an application that actually tells you more about this. But sometimes in the exam, they'll ask you why evaporation causes cooling, which actually they are trying to ask you to explain how it occurs. So why evaporation causes cooling, you need to talk about how evaporation occurs. Okay, so that's the part. Okay, it's not really talking about here. All this is just an elaboration on the cooling effect of evaporation. Okay, I say again, this part here is actually an elaboration. It's a further explanation of the effects of the cooling caused by evaporation. Okay, but normally what we are requesting you to write is actually this big chunk of stuff here. So do take note of it. Okay, and with that, we have come to the end. So key ideas behind evaporation is that evaporation causes cooling, what we have mentioned. Occurs when the molecules of the surface escapes into the atmosphere. So there are two things that they must overcome: the force of attraction between the particles, and they must overcome the atmospheric pressure. Very similar to boiling actually. Okay, in terms of the things they must overcome. This one here is actually talking about the similarity and differences. Okay, sorry, talking about the differences. Okay, so do take note of this points here. Okay, so with that, in a summary, a nutshell, we talk about internal energy of a substance. Okay, this is affected obviously by whether it is being heated or is being cooled. So when energy absorbed, it's like heating. When it's being released, it's like being cooled. So when it's being heated or cooled, the energy absorbed can either go to related to potential energy or it can be related to kinetic energy. So it can only be one of this at a time. Okay, only can be one of these at a time. Cannot both occur at the same time, only one at a time. Okay, so that was all we went through a bit in details. The key ones that you must be able to describe is solidification, melting, and boiling. Okay, these are the three main ones in terms of explaining with the internal potential energy, in terms of the internal kinetic energy. Okay, and the last part that we went through was actually what happens during evaporation. Okay, and of course the differences between boiling and evaporation itself. So that was what we went through in chapter 9. It's a relatively short chapter, but there's quite a fair bit of standard answers to remember. So as you look through this chapter, right, a lot of text, but the main points, I've captured it in all these writings over here. Okay, but I felt, okay, if you ask me, really all the explanation here gives you a very good understanding of what actually happens during a change in state. So that's all for today. Okay, I'm going to stop the recording. Okay, after the stop the recording, you can ask me any questions if you have them. So yeah, let me stop the recording. Okay.